All right, so the do now here has the region bounded by the square root of x and y equals x squared. So we're talking about two functions that are inverses of one another. So here's y equals x squared, and here's y equals the square root of x. All right, now the big question that comes out of all of this is which way is better? Is it better to work with it in terms of x or in terms of y? And the way you diagnose that is making a determination of really dominance more than anything else over the interval, because we're talking about this enclosed region. Over the interval, is there a change in dominance? Well, the radical function is above the parabola for that entire interval, right? So there is no change in dominance. So that tells us that a good strategy would be to work with this in terms of x. If you were to change your perspective, it's the same idea. The parabola would be further to the right than the radical for all values of y that relate to that interval. So you could also do it with respect to y. However, this is given to us solve for y in terms of x already. Had the question been given to us solve for x in terms of y already, I would go the other way. All right, so this is one of those where it's equally easy or difficult to go either way. It's just a question of preference. So however the information is given to you, that's the way that you should decide to go. All right, I do need the intersections. So x squared has to be equal to the square root of x. Square both sides. X to the fourth equals x. Bring the x over. X to the fourth minus x equals 0 so that you don't lose a solution. X times x cubed minus 1 equals 0. So set each of these factors equal to 0 and solve. So I'm going to get x equals 0. Now, x cubed minus 1 equals 0, that's factorable, but we do know an obvious solution from that would be x equals 1. And we're definitely interested in obvious here. So 1, 1, and 0, 0. So I would need to integrate the difference between the square root of x and x squared over the interval of 0 to 1. Is expand that into the third dimension. So the what if part of it. What if emerging from the area you calculated were infinitely many squares? Well, we'll start with that, then we'll get to semicircles and equilateral triangles. You would want to know what the volume of that new solid would be if the cross sections are perpendicular to the x-axis. And so what we have to do is create a three-dimensional drawing with this diagram as the base region. Right? So the base area of a three-dimensional solid. All right. So, you know, it's not going to look anything like this, but just to give you a sense. You have a three-dimensional solid, and this is just a cone, but when I say the base area, I'm talking about the bottom part of it, right? The area created by that base. So the base for this figure will be that little leaf-looking thing, all right? But what I have to do is I have to draw that in such a way that that looks like a base, and it allows for squares to emerge from it, all right? So it's more of a perspective drawing. So I'm going to make this my y-axis, with this being my x-axis. So I'm going to draw my y-axis on a slant. All right, so vertical lines are going to be parallel to this new way of drawing the y-axis. All right, so I need to draw the parabola and also the root function. All right, so I mean, you can do it by points if you want, but you could also just kind of ballpark it. It's equally challenging either way, I think. So since we only need the part in the first quadrant, what I'm going to do is I'm just going to make it a nice wide curve. So there's my y equals x squared. I'm really just going to kind of exaggerate it. Same thing with the root. All right, so it's supposed to kind of look like, I mean, you know what my drawing skills amount to, but it's supposed to kind of look like you're taking the graph and sort of laying it as best you can horizontally. Right? So emerging from this, we have to draw infinitely many squares. So somehow we got to get infinitely many squares in this interval. All right, that sounds easier said than done. So how about instead of that, we just draw one? Like, if we can handle drawing one, then maybe we'll get a sense of how this is supposed to go. Yeah? Well, it's dangerous territory. Well, because that's where I park. So if you took my spot, we'd have issues. Somebody did one year. I pull in and there's a Jeep in my spot. And I'm like, oh, you're out of your mind.
Is there like unassigned spot?
Everybody knows where my spot is. Yeah. It's very clear.
Where is it?
All the teachers know.
It's right by the speed bump. Like as the buses pull up. Yeah. It's for the fast exit out of the L building. So. Anyway, nobody takes my spot. I toyed with the idea of spray painting my name on it, but I didn't think that would be allowed.
Wait, 10 or 10?
I was going to go T-can, but
nice.
different possible options. Yeah, T-can 290.
You pull up and you see
Yeah, I'm sure somebody would speak to me. They'd give me a hard time, I think.
like 10. Can Parker? Can I?
Yeah, oh, yeah.
Student must be pranking us.
Either that or they have so much respect for me that they, you know, I'm kind of a big deal around here.
Great. Can on every car.
So, anyway, let me draw the rectangle. I'm sorry, the square.
Senior prank should be a senior skip day. Again.
Don't get me started on senior skip day. Anyway, so if I have a square just kind of standing out or popping out from this base area, this would be the base of that square. And so I have to give it some height. Square.
Where have you been?
It's a lot like a rectangle. Oh, I see. It's from like an angle. Yeah.
Oh, I finally
Yeah, what we're doing now.
I can't draw that.
read.
How do I draw that though?
Basically parallelogram.
Yeah, because it's a perspective drawing, it's going to look like a rhombus, parallelogram, depending. But yeah, it's supposed to represent a square. Now, I only drew one of them, but there's supposed to be infinitely many of them. And if you put infinitely many of those squares in there, you're going to get a shape. And that shape would have volume to it. It would be a three-dimensional figure. All right, so let me do another one. Oh, that's an eraser. So maybe I'll do like a tiny one over here. The size of the squares change depending on the length of the distance between the segments, the segments of the curve. So maybe I'll draw like a little guy over here.
I just wrote squares.
Buddy, we're getting paid by me. I think we missed it.
Or something like that. All right, now if I connect all the ridges, so all the vertices, screwed that up. And this one should have been a little taller. You're looking at something along those lines? But the more I draw cross sections in there, the more of a mess it becomes. So you're kind of better off just having it on faith that it's going to create a three-dimensional figure, and you're going to get a volume from it. But just draw the one cross section, because otherwise you kind of have to blur your vision and look at it from the correct angle in order to see what you're supposed to see. All right.
I see the world in a new light.
I appreciate that.
Yeah, I'm actually exactly.
All right, so now what we have to do is figure out what the volume of this is. All right, so in order to do that, what I need to do is figure out what the volume would be of a single cross section. So I'm going to redraw it, but this time I'm only going to keep it to one cross section. Well, it's going to involve area, but we're going to start with area and then kind of branch out from there. So here's the one cross section. Now, if it has no width, then we would just be talking about an area. But even though it's infinitesimal, there's still a width associated with it. So I'm going to bring it in and give it some thickness. I never know how to do that last bit. Okay, just believe. And actually, this should be more like that. And I'm going to color that side in because this is the important piece. All right, so each one of those rectangles has that infinitesimal thickness, right? So in order to find the overall volume, what I would want to do is find the volume of a single slice, each one of these cross sections, and then integrate them all together, all right? But in order to do that, I need volume of that single slice. Now, volume of a rectangular prism is length times width times height. All right, so off the bat, we have the thickness. We have one of the dimensions. That's going to be a dx. All right, we also have an important piece of information. These two sides, this side and this side, are congruent to one another. Well, actually, all four sides are congruent. But those are the two I'm really looking at. Because if I could figure out the length of the base, then I'll automatically know the height, all right? And therefore, I'll know all three dimensions, all right? So I just need an expression that represents the length of the base. Now, if you go back to what we did in the do now, mere moments ago, yesterday, we're looking at it in two dimensions. If I wanted to find the distance between these two curves, what would I do? If I wanted to find the vertical distance between those two curves, It's not that complicated. If I had a coordinate, let's say 1, 1 and 1, 3, and I wanted to find the vertical distance between those 2 points, what would I do? 3 minus 1, right? Subtract the y values. 3 minus 1 is 2, right? That's what I would do here also. I would subtract from the dominant function, which would be the root function, I'd subtract the non-dominant function, right? So I'm looking for the difference between the y values. So this distance here, this is going to be the square root of x minus x squared. All right, and again, that's because you have a distance here of y equals the square root of x, and the other curve has a distance of y equals x squared. Subtract the y values. All right, so now we have 2 dimensions. Well, actually, we have all 3. All right, so for my volume, I would state my length times my width, so the root of x minus x squared, times the thickness, dx. All right, so that's the volume of a slice, the volume of a single cross-section. But I want them all. All right, so if I want them all, I'm going to integrate the square root of x minus x squared dx, going from the start of the interval, which is at 0, to the end of the interval. Oh, that's terrible. That's not much better. Where is the end of the interval? 1. So 0 to 1.
Wait, why do you have to leave off the square?
Because we need to find the length in between the 2 curves. So I need to subtract the y value, the 2 y values associated with the curve. So the y value from this curve, which is the square root of x, and then the y value from that one, which is x squared. But because, so that gave us this 1 dimension, because I need the volume of this, I need base, height, and thickness, I have to take this expression and multiply it by that, which is the same as saying, take this and, oh, you're saying why didn't I square it there? Oh, that's an easier question. But if anybody wanted a complete repeat explanation, you just got it. Anyway, so that's how you set up the integral for square cross sections. So now we just have to do it for semicircles and equilateral triangles. All right. But you can see a lot of the structure is going to be the same, right? Because the base area is going to be the same. The length in between the curves is going to be the same, and the thickness is going to be the same. It's just the shape emerging from it is going to be different. All right. So instead of drawing the entire solid, what I'm going to do is I'm just going to focus on the cross section. All right. So so we're going to do a whoop, and then I want it to be whoop. I could do a better whoop. Whoop. There we go. All right, so I'm going to give it some thickness. That thickness is going to be dx. We already know that the length of the base is the square root of x minus x squared. All right, so I need the volume of a semicircle or a semicircular slice, which is really just going to be the area with the thickness. So let's even dial that back for a second. Let's find the area of a semicircle. Well, area of a circle is what? So half of that. So 1/2 pi times the radius squared. What's my radius?
Rad x minus x squared over 2.
Indeed it is. All right, so the volume of the slice is going to be all of that multiplied by dx. And again, I don't just want one of them, I want all of them. So I want to integrate all possible all possible semicircular slices on the interval of 0 to 1. So going from 0 to 1, 1/2 pi root x minus x squared quantity over 2 quantity squared dx.
For a short answer question, is it okay to leave the volume and the integral?
It depends on what they're asking you for.
Okay.
Yeah, if you needed to actually report a volume in particular units, then you'd have to go to the distance. But most of the time when it comes to questions like these, it's calculator friendly.
Yeah.
So, but in this case, it's not bad because it's reverse power rule, and the same thing with the previous one, but some of them can get a little nasty. So in a lot of cases anyway, especially for multiple choice, they're either going to ask you for the integral that would give you the volume, or you could just do it on the calculator, it'd be on the calculator part. Right. So then we want to do equilateral triangles. So one more diagram. Bring it out a little bit. All right, so my base area accounted for. Now I just need an equilateral triangle. All right, so again, we're going to have the thickness associated with it. And that thickness is dx. Now this is all from the perspective of the x-axis because it said perpendicular, cross-section is perpendicular to the x-axis. Right? If it said perpendicular to the y-axis, you do all this, but your thickness is dy. Right? So it changes your perspective and therefore changes the type of integral that you would create. Right? So a little bit of a different conversation. Not difficult or any more difficult than this stuff, but just different. Anyway, what I need is some way of coming up in a reasonable way, some way of coming up with the area of a equilateral triangle or an equilateral triangle specifically. All right. All right. Now you could use right triangle trig also if you wanted, you know, a little SOHCAHTOA. You know, you could do a little sine of 60 equals h over y. You could do it a bunch of different ways, but all roads are going to get you to this. The idea is that you want to come up with a simple expression that's going to lead you to the area. This is something that, I mean, I would commit it to memory only because you don't want to have to derive this every time, right? But it's not something that I don't think anyway. I haven't taught geometry in a while, like 10 years, but I taught it for like 10 years prior to that. So in the 10 years I taught it, there was never a moment where the students were asked to memorize formulas for specific types of polygons. It was always like, you would know the general formula for like a rectangle, maybe a parallelogram, but that was the same thing anyway, a triangle, maybe a trapezoid, unless you were subtracting triangles from rectangles in order to figure it out. But I don't recall ever asking anybody to remember specifically the area of an isosceles or a equilateral triangle or anything like that. So, you know, this may be the first time you're experiencing this, but it's something that you may want to do, because this type of question comes up often enough that it's a time saver if you know it. All right. So I know that the difference between the y values, just like the last two times we did this, is still the square root of x minus x squared. But now I can come up with the volume quickly and easily. Volume of the slice is going to be radical 3 over 4 times y squared, all right? So the y is the length of the base, right? So radical x minus x squared, quantity squared, dx. Integrate that over the appropriate interval. So from 0 to 1, all that stuff. And you have the formula that would give you the volume of the solid created by populating this base area with infinitely many equilateral triangular cross sections. All right, so pretty interesting stuff. And really, it's not overly difficult when you think about it, because it's just really a question of, can you come up with the area of the surface or the face of the figure that you're populating the base region with. Right? If you can do that, then you're in pretty good shape, because the thickness makes that area into a volume. The antiderivative integrates it, or integrates all of those volumes together to create the volume of a singular solid. Right? So, yeah. Anyway, so you have some practice problems to do for classwork / homework.